Let us continue on our quest to accurately predict the trajectory of a baseball after a home run hit. And we've seen already that real baseballs, when they're struck, can actually rise higher than the trajectory predicted by the free fall model. That's no air drag whatsoever. And of course, baseballs can also rise higher than the trajectory that one would expect with the quadratic model of drag. So there must be something missing from our model. And let's just suppose that that's some sort of upward force that for now we can call lift. So I will postulate that this force points straight up, opposite gravity. And remember, you can always pick any two perpendicular axes and resolve a vector along those axes. So why don't we pick an axis parallel to velocity? That would also mean parallel to the drag force. This is the quadratic drag. And the other axis would be perpendicular to that direction of the velocity. So here are the two components of this fictional lift force, or a postulated lift force, resolved along those two axes. But you'll notice that one of the components points in the same direction as drag. So the combined effect of this quadratic drag and then this smaller backwards force would be a net vector that just points in the same direction as the drag, but shorter. So wouldn't that mean that it's part of the quadratic drag? You see that? Any component of this so-called lift force that's opposite quadratic drag would merely subtract from quadratic drag, and then whatever's left over, you would just call that quadratic drag. So I'm being kind of circular here, or at least it sounds like I'm being circular, but the point is that's already been accounted for. Any component of the force between the air and the baseball that's parallel to velocity has already been accounted for in our quadratic model of drag. So the only other component we're interested in would have to be this perpendicular component. So our postulate here is that whatever the missing ingredient is, it's got to point in this direction, perpendicular to both the drag force and velocity, which is opposite quadratic drag. Lift force is perpendicular to velocity. That will be a very useful fact that will allow us to actually model this effect pretty simply. So this perpendicular force that we're interested in describing is commonly called the Magnus Effect. Let's let the guy from the Veritasium channel introduce some information about this effect, and many of you have seen this popular video now about the people throwing the basketball off the top of a dam.
Recently, some friends of mine went to the Gordon Dam in Tasmania, which is 126.5 meters or 415 feet high. Then they dropped a basketball over the edge. You can see that the basketball gets pushed around a bit by the breeze, but it lands basically right below where it was dropped. Now watch what happens when they drop another basketball, but this time with a bit of backspin.
Whoa, look at that go! That's incredible.
So you want those to get back in the water, do you?
This is Brett who just threw it. I literally just dropped it with a bit of spin, like I didn't even throw it, and it just took off. Like we had no idea that was going to do that.
And this is where I come in. The basketball was subject to the Magnus Effect, which affects all rotating balls or cylinders as they fly through the air. And it works like this. As the basketball picks up speed, air on the front side of the ball is going in the same direction as its spin, and therefore it gets dragged along with the ball and deflected back. Air on the other side is moving opposite to the ball spin, so the flow separates from the ball instead of getting deflected. The net result is the ball pushes air one way, so the air applies an equal force on the ball the other way.
Okay, if you do some Googling, you may find an alternate explanation, something about the air pressure on either side being different, kind of like the air flowing over an airfoil or the wing of an airplane. People often make reference to the Bernoulli effect. I think that's an erroneous explanation. From what I understand from my reading, this guy's explanation here in this video is more accurate. It has to do with the ball, or the air kind of clinging to one side of the basketball and getting pulled or deflected as it passes through to the other side. So keep in mind, if the ball is falling then from the ball's perspective, the air is rushing upwards. We've got air rushing upwards. And if the ball is spinning, which way is it spinning here?
And this is
Clockwise. So if the ball is spinning clockwise, then the right side of the ball is actually moving even faster past the air than the left side. If you look at the left side, it's moving upwards, which tends to cancel to some extent the downward motion of the ball. So to summarize, on the right side of the ball, the relative motion of the air and the basketball is greater. There's a greater speed associated with that relative motion. Over here, the relative motion has a smaller speed. And so perhaps there's more possibility for interaction between the air and the basketball. There's obviously a much more technical explanation there, but let's just go with that. The slower the relative motion between one side of the ball and the air, the greater the interaction, and hence the greater the deflection of the air.
is known as the Magnus Effect, named after Heinrich Gustav Magnus, who described it in 1852. Of course, Isaac Newton beat him to it by nearly 200 years, describing the flight of tennis balls at Cambridge College. But, you know, he's got enough stuff named after him. This effect is very important in sports like tennis, soccer, and golf. But could it have...
In this diagram, they're referring to this as a tube, as in a cylinder, but we can pretend it's something like a baseball. And you'll notice that it's moving to the right here, moving to the right, and yet rotating counterclockwise. So if this were a baseball that had just been struck by a bat, we would call that backspin. Same thing if the ball had been pitched. So since the ball is moving to the right through the air, the top side of the ball has an additional leftward component of velocity because of the rotation. And that component tends to subtract a little bit from the forward motion of the center of mass. On the other hand, the bottom of the ball, because of the counterclockwise rotation, has an additional component of velocity to the right. So the bottom of the ball actually has the greatest speed of motion with respect to the air. And that's why there's less interaction with the air on the bottom. It's the air on top that gets deflected the most. Now this diagram isn't really capturing that inequality between the top and the bottom. But I've indicated a vector here, force of the ball on the air. The ball pulls down on the air. Let's not worry about the details of that interaction. But that's the deflection that happens on the opposite side. And we know from Newton's third law that that's got to involve an equal and opposite reaction force. And there's a mistake here. This should say BA. Again, the downward force, that's the pull of the ball down on the air. And then this upward force is the force exerted on the ball. It's the air pulling up on the ball. If the ball pulls on the air has to pull on the ball, equal and opposite. So by deflecting the air downwards, the ball gets an equal and opposite push upwards. And that's, in essence, the Magnus effect. That's a force that we will be calling the Magnus force. It's a force on the ball. And they've already indicated it with this purple arrow here. That's the same as my red arrow. Here's a nice GIF that I pulled from Wikipedia. So you can see the turbulence on the backside. Presumably this would be like a ball moving to the right. And you can see how the airflow changes from being laminar, I think it's called, to turbulent behind the ball. And if you watch there we go. Yeah, I think it's kind of clear that the top, or is it clear? I have to watch this a couple times. I'm trying to decide, does the air get deflected upward or downward? Okay, the air is definitely getting pulled upward, right? If you look at the bottom. So if the air is being pulled upward, then the ball, it's probably a cylinder here, let's call it the ball would have to be pulled downward, and that's what they're indicating with this red arrow. So this is like the opposite of what we're concerned with the baseball. This would have to be a cylinder that's rotating clockwise, so it's got what you might call topspin, and it gets deflected downwards. It pulls up on the air, and hence the air pushes down on the cylinder. It's a lot like how airplanes work. You could have a much more detailed explanation, but basically the wings of an airplane push down on the air, just like when a bird flaps its wings. The wings of a jet are not flapping, well, they better not be flapping. They may look stationary with respect to the jet, but in a sense they are pushing down on the air, and hence the air pushes back up on the plane. There's your lift force. I'm going to skip around a little bit in this video, but this video will show us that the strength of the Magnus effect has a lot to do with how quickly the ball is spinning. We'll see that the faster the ball spins, the greater that lift force on the ball. So they're telling us, for starters, they've got a ball that's going to be spinning at almost 4,000 RPM, and they give us a speed here, 10 meters per second. Now that is the speed of the air moving in this wind tunnel. Remember, whether you've got a ball rushing through the air or a stationary ball with air rushing past it, the effect is the same. What's important is the relative motion. In this case, they've got a ball suspended from a rod here. It's actually a shaft that can rotate. So they can control the rotational speed of the ball, and they can also control the speed of the air through the wind tunnel. Both of those variables. So let's call those V and omega. V for velocity, and omega for the rotational speed. You see that? As soon as this ball gets spinning, evidently there's some lift force to the left. Now, of course, the ball doesn't continue to rise because as this shaft swings to the left, gravity will tend to pull it back down. So there's going to be an equilibrium between the downward pull of gravity and the lift force, which is pointing to the left. I'm calling it lift, even though in this case it's applied to the left. Now you can imagine if the lift force were greater, the shaft would swing out farther to the left before it reached equilibrium, because the higher this shaft goes, the greater the gravitational force. We haven't talked about torque yet, but just take that on faith, if you would, please, at this point in time, that the greater the lift force, the higher the angle to which this shaft will rise. So let's skip ahead. Try to make a mental note of how high that thing had risen. All right, so we've increased the RPMs just by a little bit here. Not a huge difference. Let's skip ahead towards the end of the video where they really get this thing going. Okay, this is interesting. They've increased not only the RPM but also the speed of the ball. So we're going to see that both of those variables influence the Magnus effect, or the strength of the Magnus effect. So here's a ball that's not only spinning faster, it's also moving more quickly through the air. Or really, it's the air moving quickly past the ball. Okay, I just want you to observe the qualitative relationship there. If the ball moves faster, you get more Magnus effect. If the ball spins faster, you get more Magnus effect. Here's a nice graphic showing how if a ball is not spinning, a baseball, then the wake, that's the space behind the ball after the air is kind of separated temporarily, the wake is symmetric about the horizontal axis here. But if the ball is spinning, you lose that symmetry. In the case of backspin, that's what we're looking at here, because presumably the ball is moving to the right. That's why the wake is to the left. Ball's moving to the right and it's rotating counterclockwise. That's typically called backspin, and in that case, there's a deflection of the air downwards. You can read here if you want about different types of spin. It looks like often a curve ball is given forward spin, which causes it to deflect downwards, and if a pitcher gives the ball top spin and hence causes the ball to deflect downwards, I guess that would be harder for the hitter to strike the ball. But we're interested in the case of backspin. So not only can a pitcher do that, but typically when a ball is struck from the bat, there's often backspin. You can think about it. Just imagine the ball hitting kind of the top part of the bat. It probably would have a tendency to spin backwards rather than forwards. And the backspin is what introduces that lift that will kick the ball upwards and cause it to reach a greater apex than it would otherwise. So this diagram it's something I pulled from the web, but it's basically the one we're working with. We already talked about the downward pull of gravity, This is the quadratic drag, force sub d for drag. I just called it capital D. And then we've got this perpendicular new component that I'm calling the Magnus force, and they've labeled it F sub m. So it would have the dimensions of force, newtons. Obviously, the velocity is opposite the quadratic drag, and then they're indicating with these arrows here that this ball is rotating counterclockwise with some spin rate, omega, angular velocity, omega. Okay, here's one more video.
And we thought now would be a good time for us to talk more about what that new statistic actually means called spin rate. So spin rate, as the name implies, has to do with the rate of spin or how much an object is spinning. Because as it turns out, an object traveling through a fluid such as air that's spinning actually has a new force manifest itself called the Magnus force. You probably have seen these effects demonstrated in some dramatic videos where they take basketballs, they drop them off of dams. As it pertains to baseball, however, we can think of the Magnus force acting on this baseball in the following manner. So if we take a baseball such as this, and typically we come through and we throw it like this and release it, and it's spinning thusly, we see several important characteristics. Number one, the velocity v vector pointing in this direction. And that's a measure of how hard the ball has been thrown, how much heat or how much mustard has been put on it. Pointing down, we have the force of gravity that's always there and insatiably pulling the ball downwards. Pointing backwards from the velocity, we have the force of drag, which is tending to slow the ball down as it pushes through the fluid, in this case air. We also now have the...
Notice he's simulating backspin and mustard. I don't recall seeing that anywhere in our chapters on Newton's laws.
Magnus force, F sub m, which in this case is pointing up. And there's a couple of key ingredients that we need to focus on with regards to the Magnus force. Number one, it depends on two parameters, this goofy looking W called omega, also known as the angular velocity, which happens to be the spin rate. That exactly is the spin rate, times the velocity or the translational velocity of the baseball. And we see that the Magnus force depends on these two things. So that's the theoretical model, but you might be asking yourself, well, that's all well and good.
You know, I'm sitting here thinking, do you think when this guy's driving in a convertible, do you think the top of his head experiences a Magnus effect? Well, I suppose not, unless he'd be spinning. Okay, so after that, they do a little computer simulation, which is informative. So I encourage you to check it out, man. He just threw up a formula showing how the Magnus force depends on omega, the angular velocity, and I think the formula included the speed of the ball, v. So I pulled up the Wikipedia article on the Magnus Effect, and sure enough, here's a formula that would describe the strength of the interaction. Now, as far as its direction, you can codify that too using an equation that includes something called the vector cross product, but we haven't talked about that yet, so let's just skip over that for now. They're talking about the Magnus effect on a cylinder. I guess it's a little easier to analyze the physics for a cylinder than it is for a sphere, but qualitatively the result is the same. And of course the force on the cylinder is going to depend on the size of the cylinder, like a paper towel cardboard tube rather than a toilet paper tube would probably experience more force for the same rotational rate simply because it's longer. So here they've expressed, let me get my laser pointer, they've expressed the force per unit length. So just imagine a tube that's 1 meter long. So the force per unit length would be the force on that 1 meter long tube. Evidently it depends on the density of the fluid, just like density showed up in the quadratic drag formula as well. V, the speed of the cylinder through the fluid, in this case the speed of the baseball. We already saw that in the wind tunnel video. We observed that when the ball is moving faster through the air, or vice versa, you get a greater lift force. And then this quantity they're calling big G, which is not the universal gravitational constant. They're using that letter for something else here. Strength of the vortex. You know what? A big gap in my education in physics is fluid dynamics. That's a very mathematical branch of physics with a lot of vector calculus. Not something I know a whole lot about. But for this lab, we just need to know enough to model this interaction with a force vector. Okay, and they're telling us that the strength of this vortex, whatever that is given by, let's skip over to the right side of the equation. They tell us here, omega is the angular velocity, r is the radius of the cylinder. Okay, well, if we're talking about the baseball, it would be something like the radius of the baseball. That's a constant. Omega is the only variable here. So as the ball is in flight, as it's got that backspin, the rate of spin is likely changing. But if you think about it, the baseball's in flight for only, what, 4 seconds? We've already modeled quadratic drag enough to see that the ball is in the air for about 4 seconds. So let's just approximate the motion here as if the angular velocity does not change. Let's assume that the ball leaves the bat with a certain rate of spin, and yes, there's going to be friction with the air that will probably decrease that rate of spin, but we'll just pretend it's constant. Keep things as simple as possible. And it turns out we can still pretty realistically model the motion of the baseball, even without knowing exactly how omega depends on time. But the important conclusion here from this first equation is clearly that the Magnus force depends on speed, and it's speed to the first power. There's no v squared here like there is for the quadratic drag. So we would say that Magnus force is proportional to the speed. So here I'm talking about magnitudes. There's no arrow here. This is the length of the Magnus force vector. This is the length of the velocity vector, otherwise known as speed. And then this g term contains omega, which shows up also to the first power. So evidently the Magnus force is also proportional to the first power of angular velocity. So let's see if we can incorporate that into our Excel spreadsheet. And we will pretend that omega is a constant. And before we do that, we have to talk a little bit about this thing called the scalar product. We'll go into more depth later in the semester, but we've looked at how to add vectors, subtract vectors. You may wonder, is there a way to multiply vectors? Well, there's more than one definition for vector multiplication, but probably the most useful for our purposes is the so-called scalar product, also known as the dot product. So here are two vectors which I've resolved into their Cartesian components. And if we'd like to multiply or dot these two vectors, here's one way of doing it computationally. You just take the x components of the two vectors, multiply those together, then you take the y components, multiply those together, and add those two terms up. That's it. X components multiplied, y components multiplied, added up. For example, if my vector A had an x component of 3, so go 3 to the right, 2 up, then the x component would be 3, the y component would be 2 for vector A, and for vector B, the x component would be 4, and the y component would be -1. In order to compute the dot product, first you multiply the x components together, that's 3 times 4, and then you multiply the y components of the two vectors together. Okay? Multiply the x's, multiply the y's, add them up, and you get 10. Notice that's a scalar. I put two vectors in, one scalar comes out. This is reminding me of Thunderdome, Mad Max Thunderdome. Two vectors enter, one scalar leaves. Hence the name scalar product. The vector product, which we'll look at later in the semester, involves two vectors going in and one vector coming out, hence vector product. That's also called the cross product. Okay, here's another example. Vector A, 2 to the right and 2 up, so it's going 45 degrees here. Vector B is 2 to the left and 2 up, also 45 degrees, but the other way. What happens if we dot those two? Well, the x components are 2 and -2, so I've multiplied the x's together, I've multiplied the y's together. Wait a minute. What have I done wrong here? Yeah, this is supposed to be a 2. Oh, how did I not catch this? Let me fix this. Okay, let me try that again. Vector B is 2 to the left and 2 up, so the y component is still positive. And when we dot the two vectors, yes, we find that the dot product is 0. So let me point out the fact that these vectors, if you place them tail to tail, you can see that they are perpendicular because this one goes off at 45, this one also goes off at 45. They're perpendicular and their dot product just happens to be 0. So I've only got time to show you one example here, but that ends up being a rule. Anytime two vectors are perpendicular, their dot product is 0. And you can check that with our famous basis vectors, I, j, and k hat. I hat and j hat are obviously perpendicular. Here are their full x, y, z components. And you can see that when you go to dot these two vectors, you multiply the x's, you get 0, multiply the y's, you get 0, multiply the z's, you get 0, add all that up, of course it's still 0. So you can take any pair amongst these three and their dot product will be 0. So try to memorize that the dot product of two orthogonal vectors is 0. Yeah, I've written that right here. The dot product of two perpendicular vectors is 0. Okay, back to our baseball. Well, we've already established that the lift force we're interested in should be perpendicular to the velocity vector. So if we know this vector that we're seeking is perpendicular to v, then what should happen when we take the dot product of the lift force or the Magnus force with velocity? We should get 0. So I've broken the velocity into its horizontal and vertical components, and I've written that here, x component, y component. And watch this clever or not so clever device. There wasn't even any theory necessary. It's just like by inspection, you could say, I have found a vector that happens to be perpendicular to v. So I've drawn it perpendicular, and you'll notice that the x component of this vector, which you can tell is negative. See how the x component points off to the left? By design, I've chosen it to be equal to the negative of this component. See how this length, at least I try to draw it this way, this length is the same as this length. But because it points off in the left direction, I have to give it a minus sign. So this component is the negative of the y component of the velocity vector. Try not to be confused here. This vector is not v. This is not the velocity vector. I didn't want to name it because we're not going to get too attached to the name of this vector. But this vector has an x component equal to the negative of the y component of the velocity vector. And you'll notice that the y component of this vector is equal to the x component of the velocity vector. Okay? So this component, absolute value and a sign, is the same as this component. And this component has the same magnitude as this component, but the opposite sign. Why am I doing that? Well, what happens when we dot this vector with this vector? I've done that right here. The x component of this second vector is negative vy, and the y component of this second vector is vx. It's the x equal to the x component of the velocity vector. And the rest just do in your head. You know how to dot these vectors now. You multiply the x components together, multiply the y components together, add, and you get 0. Do you see why? We have the same product for the two terms, but one of the products has a minus sign. So maybe you see now why I had the foresight to choose this particular vector, because I knew that when I take the dot product with the velocity vector, I would get 0, and hence this vector has to be orthogonal to v. So we've at least found one vector that points in the direction we want. We can easily relate this desired direction to the velocity vector. Now let's just check something. If the ball really is flying off in this direction, wouldn't its x component of velocity be positive? And we know that this vector, which kind of tilts back, needs to have a negative x component. So actually what I should have said was, let's look at the y component of the velocity vector. It does point up. So we know that v sub y in this diagram is a positive number. Over here, the negative of v sub y would then be a negative number, which makes sense. It needs to be negative. This vector is tilted backwards, so we know that its x component needs to be a negative number. And the reason I'm pointing this out is there's another choice here. Another vector perpendicular to v would be the one that points down like this. Do I have a graphic for that? No, I don't. So imagine this vector going down like this. All you would have to do is move the minus sign from here to there. So instead of using this vector, I could have put the minus sign here, and I would still find that the dot product is 0. But that would be the vector pointing off like this. We don't want that force because we're imagining that the baseball has backspin, so it should get a lift upwards. So this is the appropriate vector, at least for the direction. Okay, so those two vectors have to be perpendicular because their dot product is 0. Now, we want a vector that actually has dimensions of force. Yes, it needs to point in that direction, but it's not enough just to arbitrarily, because you'll notice it would have the same magnitude as the velocity. if we use Pythagorean theorem, and we don't necessarily know that the force vector is going to have the same magnitude as the velocity. So there's a bunch of stuff that the Magnus force will also depend on, including the spin rate of the ball. I'm just assuming that all of that stuff is a constant. It's just a bunch of constants that go into those parentheses out front. This is what gives us the correct direction. Now, we know how to turn force into acceleration, because in the Excel spreadsheet, we're dealing with the acceleration. We integrate that twice numerically. How do you turn force into acceleration? Well, if F equals ma, then A equals F over m. So all we have to do is divide the Magnus force by the mass of the baseball to get the so-called Magnus acceleration. So gravity contributes an acceleration of 9.8 downwards. A quadratic drag contributes an acceleration that's opposite the velocity. And now we've got this Magnus effect, which contributes an acceleration perpendicular to the velocity in a direction that we call lift. But the point is, even after you divide by m, all this garbage out front is just a bunch of constants. Okay, so we can absorb the m into the parentheses, and there's just a whole bunch of terms here that have to do with the air density, the spin rate of the ball, the mass of the baseball, probably some other stuff. You know, you have to take a more advanced class on fluid dynamics to learn more about that. But the point is that for our purposes, we treat all of that stuff as constant. These numbers are not constant, because as the ball is in flight, the velocity of the ball is constantly changing, and that includes both components of the velocity. So this stuff doesn't change, this stuff does change. Let's agree to call all this junk inside the parentheses alpha. And that's specific to this class and this lab. You won't see that outside this lab. It's just to make things cleaner right now. Let's just agree to call all this garbage alpha, and in my spreadsheet, I will refer to alpha as the Magnus parameter, because all we're going to do is just guess. You will literally guess a number for alpha and then just keep tweaking it in your spreadsheet until you reproduce the desired trajectory. But the reason it's going to work is because we've written the acceleration as correctly being orthogonal to the velocity and proportional. Because check this out. I mentioned just a moment ago, if you apply the Pythagorean theorem, how would you find the magnitude of this vector? You do the square root of this squared plus this squared. Of course, you could then just switch the order. Well, this is the same as speed, right? So this vector is not the same as the velocity vector. It points at right angles, but it has the same magnitude. See in the picture here? This vector is the same length as velocity. It's just been rotated by 90 degrees. So the overall magnitude of this vector is speed, the length of the velocity vector, times this extra junk out front, which I'm calling alpha. And so we've correctly discovered, or we've discovered an appropriate vector that describes the Magnus force, because we know from the little videos that we watched that Magnus force is proportional to how fast the baseball is moving. And this choice of model for Magnus force correctly incorporates that. So I will remind you that in part 1 of the instructions, we arrived at this formula for the two components of the ball's acceleration. This is for free fall with quadratic drag. That's actually that's like an oxymoron, isn't it? If we've got quadratic drag, then it's not really free fall. Okay, sorry about that. This should just say with quadratic drag. In the vertical direction, we've got the influence of gravity and the influence of the quadratic drag. In the x direction, only the influence of quadratic drag. And now, let's introduce the so-called Magnus acceleration. That's the final component, which should help us most accurately reproduce the trajectory of a home run hit. So there you go. I've plopped those in. And please note, while both x and y include an alpha, notice that for the x component, we've got a minus sign here. And in the x acceleration, we actually have the y component of velocity. So it's easy to goof that up in your spreadsheet. Yes, for the quadratic drag, a sub x involves av sub x. But for the Magnus term, the x acceleration actually depends on the y component of velocity. That's because of the orthogonal nature of Magnus effect and velocity. Down here in the y component, the Magnus term depends on the x velocity, and there's a plus sign. So refer to these complete formulas. This is the whole enchilada here. when it comes time to graph your home run hit with quadratic drag and Magnus Effect, this is the formula to which you will refer. And I think it's time for me to demonstrate that. So we're back at the fictional Blueberry Stadium, examining the hit by Bubba Gump, not a real baseball player. And I've already shown you in the previous video how to produce the free fall trajectory as well as the quadratic drag model. And what we're missing now is the one with Magnus. So the data that I got from StatCast or whatever, I converted feet into meters, and I found that the true apex was 27 meters. We could see 27 is up here. So that ball actually went even higher than the free fall trajectory and certainly higher than the quadratic drag model. So we know what our target is. We need to get up to 27 meters, and we should end at 127. See how the quadratic drag plops the ball down at like 100 meters. In actuality, it would go significantly further with that lift because of the backspin. So let's see if we can account for that. Now, I've already gotten started with the last section here. See, this says quadratic drag with Magnus, so I already entered my initial components of velocity, and I started the numerical integration process, which I described in the previous video, so I'm not going to go over that again. But let's take a look here. Oh, I just gave away. Let's pretend that I don't actually know what the appropriate Magnus parameter is. I'll just leave it blank for now. Notice I'm calling that alpha. And the x component of acceleration now, I've already got the quadratic drag term entered. Here's where I need to enter or add the Magnus effect. So just a moment ago we saw that the Magnus term for the x component has a minus sign, and then this unspecified parameter alpha, don't forget to hit F4 so that we're doing an absolute cell reference. We're always going to refer back to that same alpha parameter. And then the x component of acceleration for the Magnus term really is proportional to the y component of velocity. So I will click on the y component of velocity at that same time. Remember, the acceleration at any point in time depends on the velocity at that time, because that's what Newton's second law says. F equals ma. The acceleration of the mass at any time depends on the force at that time, and the force depends on the velocity at that time. So I'm clicking on the velocity in the same row, v sub y. And then for the y component of acceleration, that had a plus sign, and it was alpha times the x component of the velocity. So Magnus parameter F4 for absolute cell reference times v sub x, and then I hit enter. Okay, now I'm going to just double click everywhere and hope that it all works out. Double click. Let's see what happens. Woo. Okay, that's obviously not realistic. Wouldn't it be awesome if your baseball did that? Oh, think of the money you could earn. Okay, well, evidently I've done something wrong because that doesn't look at all realistic. What was my error? Let me go back and check. I'm pretty sure these are right. Yeah, I'm checking the numerical integration here. So what did I do wrong here? Minus B10. Oh, right. It's because I didn't enter a parameter yet. I've got 0. That's kind of interesting. So let me just guess something like 1.0. That's the most obvious guess. Oh, that's really cool. I wish I could do that. I wish I could hit the ball, period, but this would be even cooler. Not realistic, right? Okay, let's bring it down to 0.5. So this isn't particularly scientific. I'm literally just guessing numbers. 0.2. 0.1. Okay, now I'm getting suspicious because I've already done this and I know that 0.15 was a decent value and the ball's not doing anything sensible. So I'm going to pause and figure out what I did wrong with my formula here, because it's not Newton's second law that's misleading us. I think I found my error, and you may have noticed it as well. In the y component of the acceleration, when I went to enter the Magnus term, I neglected to actually click on cell B10 here. So B10. F4. Oh, and I need that asterisk. Maybe I forgot that in the X component as well. Excel needs the asterisk for multiplication. Okay, now I'll have to double click again to update. There we go. Beautiful. Okay, now it just happens. It happened to have ended the trajectory at the appropriate place because I already extended the time interval. But you're going to find for the quadratic drag, you probably only let the ball go in flight until, what is this, roughly 4 seconds. So let me chop off this excess data here. If you only compute the trajectory for the same amount of time that you did for free fall and quadratic drag, it's not going to hit the ground. Again, we know that lift puts the ball in the air for longer. So it's going to be up to you to continue the calculations for longer. And you know what? There's some keyboard shortcuts I discovered. Is it control down arrow? Yeah. So if you hold down control and hit down or up, you can automatically skip to the beginning and end of the spreadsheet. So I'm going to hit control and then up. Okay, that took me to the last line. If I hit control up again, it takes me all the way to the top. That'll save you some time. Now, of course, you can scroll with your mouse wheel, but there's also the page down and page up buttons. So I'm tapping page down. Okay, now I've already forgotten which rows or which columns I'm dealing with. Dang it, so control up. I need to lengthen which columns here? From column J onwards, okay? So control down. Takes me to the last row. Okay, so I'm just going to hover, click and drag, and remember, since we're going with, what is it, 100th of a second time intervals, every, like row 500 is basically 5 seconds. So let's give it a couple extra seconds in the air. I'm going to go all the way up to row 600. That should be around the 6-second mark. Hopefully that's enough to get the ball back on the ground. Double click, and a lot of these numbers will continue to update as you iterate the rest of the columns, because remember, each of these quantities depends on the other quantities. How do we know when the ball has struck the ground? That's when the y coordinate, which is row K or column K, that's when the y coordinate gets to 0. So you see the ball is still rising. Now it's going back down. When does the ball strike the ground? Aha. Right here at row 583. So you could do 583 or 584, doesn't matter. Row 583. So I'm going to right click on one of these data points, go to select data. Let's edit quadratic drag with Magnus. You can see I've already entered this data series. So I didn't show you that step in this video. Let me edit this. Okay, yeah. It's already, I guess it's already done. I'm confused. I must have already done this and it remembers. Okay, so I hit OK. Row 583 was already in there. Okay. Now this one is falling short, so let's fix that one. Let's figure out what row. No drag is columns H and I. Okay, when does the y coordinate would be column I. When does the y coordinate go back to 0? Probably making you dizzy here. Okay, so it hasn't gotten there yet. We need to extend these a little bit longer. So this is the tedious part. Okay, evidently before then, this looks like it's row 468. So I can go back up to the graph. Yeah, okay, I see what's happening. When I click on that cell, somehow Excel figures out what the appropriate row is at which to end. So you'll have to do that yourself. You'll have to scroll down, figure out the row at which the trajectory has reached the ground, go into the plotting options, and make sure that you plot out to that row for each of these trajectories. I don't care if you go a little bit past the ground, just make sure it goes to the ground so that you can see what the range was, so to speak. Okay, now I had the benefit of foresight. I knew that a Magnus parameter of 0.15 worked pretty well for my data. But let's say I had started with 1.0. Interesting, still get that loop-de-loop. Even weirder, 0.5. That is so physically unrealistic. You may be wondering, what is it doing? I think I know. We're assuming that the ball is always moving kind of forward and up, and that's why we chose the appropriate lift force. But I think if a ball actually started to move like backwards, the Magnus force would change, or maybe the spin would change. I'd have to think about this some more. But if you assume a constant backspin, you would get this weird behavior that we see here, because the math doesn't lie. We know baseballs don't do that. Okay, but by the time I get down to 0.2, you can see we're looking pretty realistic here. This apex, you'll notice, is over 30 meters. That's too high. So I just kept tweaking my Magnus parameter here. We're under 25, not high enough. Okay, so 0.15 worked pretty good. This apex looks like it's around 27 or 28. And the range here, the horizontal distance, is between 120 meters and 130. It looks like it's around 138. Am I doing that right? 136. And check it out, the true distance is 127. That's not a coincidence. I already fiddled with this. Your numbers will be different. So suppose, excuse me, suppose I had gone with a different air density, like 1.3. This apex is not quite right, and nor is the distance. So if I want to increase the lift to bump that apex a little higher, let's try 0.17 for the Magnus parameter. That looks about right, 0.17. But now the range is no good. It's short of 120, and we know that the true distance is 127. So that's why I chose to go back and fiddle with the air density. In fact, there's a couple things you could tweak. You could tweak the drag coefficient, because that's that 0.3 that the website recommended. That's approximate anyway. So my advice to you is the figures that you know were accurate, leave those. Don't change the speed off the bat or the ball mass, because that's a pretty restricted value anyway. You can fiddle with the air density, the drag coefficient, and the Magnus parameter. Everything else, just leave it as is. And try to reproduce the actual trajectory so that the apex is correct and the true distance is correct. Or I should say the distance. True distance refers to the actual hit distance. Just try to get those two numbers predicted correctly in your graph, and then make sure that all of the numbers you've chosen are legitimate. Like, you shouldn't have an air density of 2. That's way too high. You can just Google the range of common air density values, make sure you're in that range, and make sure your drag coefficient is reasonable. Like 0.8, that's way too high. It should be around 0.3, 0.4, maybe as high as 0.5. Okay, so it shouldn't take you too long with a little trial and error to figure out which of those adjustable parameters will give you an accurate trajectory. And then, using the very physically motivated quadratic drag model and this new Magnus term, you can accurately predict the trajectory of a baseball. Now, the last thing I'll say is when it comes to your graph, you can change a couple things like, let's see, right-click, format data series. Okay, if I go into here, marker. I changed mine to a solid line instead of a whole bunch of dots that are connected. And you can adjust the thickness. Like, that looks silly. I went with the thinnest line I could get. And you can adjust the colors if you want, but it should automatically throw up a legend for you. And you're going to need that so I can tell which trajectory is which. It should be obvious, but anyway, I don't think I'll bore you anymore. That should be sufficient for the instructions. Just make sure that you've got the hitter's name and the stadium listed here and the date from your StatCast or the ESPN home run tracker PDF. tell me what the true distance was and the apex. Make sure you've converted into meters as I've done here. That way I can compare with the axis and see if you've successfully reproduced the apex and the true distance. That's it.